Hello, my name is Deng Lifu. I'm an undergraduate student at University of Electronic Science and Technology of China. The paper I will presenting today is titled Design a Five-Stage Pipeline RISC-V CPU and Optimize its ALU. And then I would like to share the PowerPoint to you. Okay, RISC-V is an open source instruction set architecture. In contrast to most instruction sets, the RISC-V instruction set is free to be used for any purpose, allowing anyone to design, manufacture, and sell RISC-V chips and software. I would like to introduce the outline of today's theory. It will be divided into four parts. Choosing instruction, the whole structure, the optimization of ALU, and also the implementation of pipeline. To begin with, I would like to introduce the chosen instructions. As we can see from the picture that I picked 37 pieces of RV32I instructions and a piece of multiplexing instructions. The RISC-V instructions can be divided into 6 types. For example, R type is responsible for logic and algebraic calculations. Then I would like to explain the whole structure of this CPU. We can see from the picture that this is the basic structure of a single cycle RISC-V processor. And this is a picture of RTL graph of a RISC-V CPU, which was generated by Vivado. And this CPU contains two external storage modules, including instruction memory, which was responsible for storing instructions and reading them according to the value of PC. And there is also a data memory, which was used to store data. And this data can be read by L instruction and written by S instruction. In addition, I'm going to share the data path design. We can see that there are 4 main paths inside the data path. The ALU is the part of the CPU that is responsible for performing arithmetics and logical operations. It receives the value of 2 registers as input and produces an output based on the function codes of instruction. ALU can also set condition codes for subsequent branching instruction. Decoder is responsible for splitting the read instructions and decoding them into opcodes, control codes, intermediate numbers, and other parts for use by other modules in CPU. A branch is the part of CPU that is responsible for implementing conditional jumps. It determines whether the branch condition is met based on the conditional codes of instruction and the value of 2 registers, and calculates the destination address based on the intermediate number of the instruction. If the branch condition is true, write the target address to program counter. Otherwise, add 4 to program counter and continue to the next instruction. A register is the component of the CPU that stores temporary data or address. The RISC-V-based ISA contains 31 general purpose register X1 to X31 for storing integer numbers. Register X0 is hardware to be constant 0. There is also a user visible program counter PC register that stores the address of the current instruction. Then goes to the control unit. The control unit is a component of the CPU responsible for generating control signals. It determines the type, format, and function of the instruction according to the operation code and the function code of the instruction, and generates the corresponding control signals for controlling the work of other components. Then I would like to introduce the optimization of ALU. I optimize it by replacing part of the calculation model in the ALU. The adder, I designed a 32-bit carrier look-ahead adder, and the shifter I optimize with a barrier shifter. Then I optimize I using boost algorithm combined with voice tree to optimize the multiplayer. If we want to design a high performance 32-bit adder, we can theoretically generate all SI and CI at the same time. But makes the circuit structure very complex and greatly increase the fan-in and fan-out of the circuit, which is not feasible in actual design. Therefore, I firstly designed a 4-bit super carrier lookup adder, then use four 4-bit carrier lookup adder to achieve a 16-bit carrier lookup adder in parallel, and then use two 16-bit carrier lookup adder to achieve a 32-bit carrier lookup adder. And the carrier lookup adder without waiting for the carry signal of the previous bit. This reduces the propagation delay of the carry signal between the full adder and increase the speed of the adder. And a barrier shifter is a digital circuit that can shift or rotate a data word by any number of bits in a clock cycle, which has following advantages. It can connect the input data word directly to the correct position of output without multiple clock cycles. This increases the speed of the shifter and reduce lateness. And it also can realize different shifting or rotating function according to the control signal, such as logical left, logical right, arithmetics right. The report that we can get information that the resource utilization of barrier shifter is also lower than the normal shifter. Then the waveform plot here shows the after optimization, the additional operation and the 3 shifter operations can achieve correct results. The boost algorithm and the Wallace tree are two commonly used digital multiplexer design technologies that have some following advantages. Boost algorithm is a multiplexing algorithm that utilizes two's complement to reduce the number of partial products, thereby reducing the complexity and the delay of multiplayer. Wallace tree. A Wallace tree is a multiplayer structure that uses a compressor to divide the additional of partial products into multiple levels and use a compressor in each level to reduce the number of the bits of the partial products in parallel. The Wallace tree can efficiently reduce the area and the power consumption of multiplayer and increase the speed of the multiplayer. And the simulation results can show that the multiplexing can run successfully. Implementation of the 5-stage pipeline, which stores the signals that need to be passed by each stage by adding multiply register to the CPU. Which is this is the overall code structure of a pipeline. If we represent the address stage followed by the decoding, extraction, fetch, and the write back stage. The 5-stage pipeline can can make 5 instructions execute in parallel, which can efficiently shorten the clock cycle and improve efficiency. And this is the simulation results that shows the 5-stage pipeline runs successfully, and the calculation results are also correct. And that is all for the sharing.